The Evolutionary Powerhouses, Mastering Multi-Objectives in Algorithmic Design in the Ever-Evolving Landscape of Computational Problem-Solving. Optimization algorithms have emerged as indispensable tools that bridge the gap between theoretical mathematics and practical applications. These sophisticated techniques enable us to find optimal solutions when faced with complex decision-making scenarios involving numerous variables. This exploration delves deep into the realm of multi-objective optimization algorithms, which tackle problems where optimizing one objective might compromise another. From engineering design to financial portfolio management, these algorithms provide robust frameworks for achieving balanced trade-offs among competing goals. Foundations of multi-objective optimization. At its core, multi-objective optimization deals with situations where we aim to optimize two or more conflicting objectives simultaneously. Unlike single-objective problems where there's typically one best solution, here we encounter Pareto frontiers consisting of non-dominated solutions. The mathematical formulation often involves minimizing/maximizing several functions subject to constraints. This introduces complexity since improving one aspect may degrade others, requiring careful consideration during algorithm selection and implementation. A key concept is dominance relations between solutions. A solution dominates another if it is better in at least one objective without being worse in any other. Understanding this relationship helps guide search processes effectively towards diverse yet high-quality solutions. The challenge lies in finding an approximation of the entire Pareto frontier rather than converging to a single point. This necessitates specialized algorithms capable of maintaining diversity while ensuring convergence toward optimality across multiple dimensions. Pareto optimality. Solutions are considered Pareto optimal if no other solution exists that improves one objective without worsening another. Diversity preservation. Maintaining diversity ensures coverage across different regions of the Pareto frontier for meaningful trade-off analysis. The landscape of multi-objective algorithms. Various approaches exist within the field of multi-objective optimization, each with distinct methodologies for navigating complex problem spaces. These range from evolutionary strategies inspired by natural selection to decomposition-based methods that simplify multidimensional problems. Evolutionary algorithms represent a significant class due to their ability to handle nonlinear, discontinuous landscapes efficiently. They operate through mechanisms such as mutation, crossover, and selection mimicking biological evolution principles. Non-dominant sorting genetic algorithms, NSGA2, stand out as prominent members of this family. Their effectiveness stems from incorporating elitism and crowding distance metrics to maintain population diversity. Other notable classes include indicator-based evolutionary algorithms focusing on scalarizing objectives using performance indicators, and reference point-based approaches aiming at approximating desired regions along the Pareto frontier. Mechanisms behind effective search strategies. Successful navigation through multidimensional problem spaces requires well-designed search operators that balance exploration and exploitation. Too much emphasis on either can lead to premature convergence or stagnation in local optima. Hybridization of various search mechanisms has proven beneficial in overcoming limitations inherent to individual methods. For instance, combining differential evolution with particle swarm optimization enhances global search capabilities significantly. Adaptive parameter control allows algorithms to dynamically adjust parameters based on current population characteristics. This responsiveness increases chances of discovering superior solutions throughout the search process. Surrogate models offer promising avenues by replacing expensive evaluations with cheaper approximations. When dealing with computationally intensive simulations typical in real-world applications. Evolutionary computation techniques. Genetic algorithms serve as foundational building blocks for many modern optimization techniques through their principled approach resembling Darwinian evolution dynamics. Crossover operations facilitate knowledge transfer between individuals by recombining features from parent solutions. Mutation injects randomness necessary for exploring new areas within the search space. Selection pressures determine which individuals propagate their genes further. tournament selection offers flexibility by allowing controlled competition among candidates before choosing survivors. Differential evolution introduces variation via vector differences applied across populations, providing robustness against common pitfalls observed in traditional GA implementations. Meta-heuristics for complex problem-solving beyond classical evolutionary approaches lie broader categories known as meta-heuristics, general-purpose strategies designed for tackling intricate combinatorial challenges beyond conventional analytical means. Simulated annealing draws inspiration from metallurgical cooling processes to escape local minima effectively through probabilistic acceptance criteria governed by temperature schedules. Ant colony optimization leverages pheromone trails left behind by artificial ants traversing graphs representing potential solutions paths weighted according to heuristic information quality. Taboo search employs memory structures recording recently visited states, preventing revisits, thus encouraging movement towards unexplored territories, avoiding cyclic behavior patterns. Evaluation metrics and performance assessment. Selecting appropriate evaluation metrics plays critical role in determining success of any optimization endeavor, particularly when comparing alternative algorithmic choices systematically. Hypervolume measures volume dominated by obtained solutions relative to specified reference points, serving as effective yardstick assessing both convergence and spread characteristics simultaneously. Spacing metric evaluates distribution uniformity among generated solutions, highlighting disparities indicative of inadequate diversity preservation efforts during execution phases. Generational distance quantifies proximity between approximate fronts extracted numerically versus true Pareto set, offering insight regarding accuracy achieved despite inevitable approximation errors present inherently. Applications across disciplines. Multi-objective optimization finds applications spanning vast domains including aerospace engineering, healthcare analytics, sustainable energy systems development, etc., demonstrating versatility applicable universally wherever trade-offs occur naturally between competing priorities. In automotive industries, designers employ these techniques, optimizing vehicle crashworthiness alongside fuel efficiency requirements, balancing safety standards against environmental regulations demands concurrently. Financial institutions utilize them, constructing diversified investment portfolios, maximizing returns while mitigating risks, appropriately addressing investor expectations aligned with risk tolerance levels predefined initially. Environmental scientists apply these methods, analyzing trade-offs between economic growth indicators versus ecological impact assessments, helping policymakers formulate balanced regulatory decisions benefiting society holistically over timeframes longer than immediate gains. Focus. Future directions and emerging trends. Ongoing research continues pushing boundaries through integration of machine learning paradigms, enhancing predictive modeling capabilities, augmenting existing algorithmic foundations, substantially expanding possibilities available. Currently limited, technically constrained environments encountered regularly today's practitioners face daily. Cloud computing infrastructures provide scalable resources, enabling parallel processing essential executing. Resource-hungry simulations involved extensive parametric studies, required validating novel ideas, proposed theoretically often impractical testbeds lacking sufficient capacity, locally accessible, traditionally constrained researchers operating under budget restrictions frequently experienced early career stages. Professionals encountering these hurdles commonly observed industry settings too. Quantum-inspired optimizations represent exciting frontier, exploiting quantum mechanics properties, potentially revolutionizing speed efficiencies, achievable classic counterparts, though still maturing stage, warranting cautious optimism considering theoretical promises yet unproven practically viable implementations available, publicly demonstrated successfully resolving benchmark problems, accepted academically established communities evaluating rigorously, results submitted periodically. Conferences, special sessions devoted exclusively exploring intersections, emerging fields converging rapidly, accelerating innovation rates, unprecedented historical contexts observed previously. Advances in hardware technologies coupled with algorithmic refinements promise continued improvements, increasing accessibility, making powerful tools previously reserved experts now reachable wider audiences, empowering grassroots initiatives, driving progress from bottom-up, fostering inclusive ecosystem, conducive collaborative spirit, promoting shared knowledge, advancement benefits everyone involved regardless background, expertise level attained hitherto. Conclusion: mastering multi-objective optimization algorithms equips practitioners with versatile toolkits, adaptable diverse scenarios demanding simultaneous satisfaction, multiple interdependent conditions prevalent modern world. Characterized rapid technological advancements, constant flux shaping evolving landscapes, continuously adapting needs arising, unforeseen circumstances challenging status quo, prompting need innovative responses, ensuring resilience, future uncertainties ahead. To stay competitive in this dynamic environment, continuous learning remains paramount. Engaging actively within professional networks, attending workshops, mastering latest developments, implementing cutting-edge practices, routinely testing hypotheses, empirically verifying claims, scientifically substantiating assertions, establishing credibility, enhancing influence, contributing positively, greater good, communities served faithfully, consistently demonstrating commitment, excellence, integrity, transparency, expected leaders, inspiring followership, paving pathways toward brighter tomorrows. Collectively achieved collaboratively.